Hi, we are from Group 10. My name is Long. Today we are going to discuss increasing the refining yield in oil residue stream processing. So here's my group member. I'm Rowan.
I'm Vincent.
And Iteng.
I'm Ewan.
Hi, my name is Rowan, and today I'll be discussing about the solvent deasphalting process to improve the yield of vacuum residue processing. Solvent deasphalting is a process where asphalt is separated from the vacuum residue, yielding deasphalted oil, or DAO for short, which can then be subsequently sent to following processing units. Asphalt, or bitumen, is a sticky, black, and highly viscous fluid and is normally used in the construction of roads. In this process, a paraffinic solvent, primarily propane or butane, is injected into the deasphalting tower along with the feedstock, which is vacuum residue. The asphalt-rich paraffin flows out from the bottom and the DAO-rich paraffin flows out from the top. The process occurs at elevated pressures to maintain the solvent in the liquid phase. Next, strippers remove the solvent from the DAO and asphalt using steam, yielding the products from this process. Based on research, the yield of DAO may be increased by adding coal tar into the vacuum residue before going through solvent deasphalting, as shown in the graph. The top curve represents the solvent extraction done using 30% coal tar. Besides that, adding coal tar also has numerous other advantages, most notably removing sulfur and heavy metals such as nickel and vanadium. Blending the vacuum residue with coal tar also reduces the viscosity, which will reduce the resistance to mass transfer in the solvent deasphalting unit, and therefore increasing the conversion of the vacuum residue.
Hi, my name is Xiang. Today I will discuss about the method to increase the yield of residue by using catalytic cracking.
Catalytic cracking is a process for the upgradations of residue. During this process, heavy feedstock are converted to lighter components such as gasoline and diesel, which are more valuable compared to their heavier counterparts. The main reactions that are involved in the catalytic cracking process is the cracking of long-chain hydrocarbon. Fluid catalytic cracking cracks low-value and high molecular weight hydrocarbons to more value products such as gasoline, diesel. Main reactions involved are crackings, where heavy hydrocarbons are cracked into lighter hydrocarbons, and dehydrogenations, where hydrogens are removed. Mainly of feedstocks are vacuum gas oil and hydrocracker bottoms. Catalytic cracking process involves three basic functions. First, reactions, where the feedstock reacts with the catalyst and cracks into different hydrocarbons. And second is the regenerations, where the catalyst is reactivated. And lastly is the fractionations, where cracked hydrocarbon stream is separated. Some of modifications and improvements of catalytic cracking process. Examples: residue fluidized catalytic cracking process, which targeting for residue feeds which are higher weight percents of carbons. A two-stage regenerator with catalyst cooling is typically used to control the higher coke productions and resulting heat. Second, deep catalytic cracking with milder second catalytic cracking process will improve the selectivity and lower the regenerator temperature and resulting in higher catalysis recovery.
Hello, my name is Iteng. I'm going to present about the improvement for the hydrocracking process to increase the yield from the residue stream processing. Hydrocracking is a process where low quality and heavy feedstock are converted into the high value transportation fuels such as gasoline and diesel. The difference of hydrocracking with catalytic cracking is that hydrocracking takes place in the presence of hydrogen gas. The advantage of hydrocracking over catalytic cracking is that it can handle more aromatic feeds and the products on them will be saturated. The reaction that takes place in the hydrocracker is basically cracking followed by hydrogenation. The residue is first fed into the feedback reactor along with pressurized hydrogen. Here, the residue undergo hydrocracking. The effluent of the feedback reactor will then enter a fractionator where it is separated into fractions, which are gas oil, naphtha, kerosene, diesel, and pollutants. The process can be improved by using a slightly phased reactor, where the catalyst is dispersed instead of fixed on a bed. This increases the contact between the catalyst and the reactant, resulting in higher conversion. Based on research, decreasing the porosity of the catalyst can have positive impact toward the conversion of the vacuum residue. Nickel and phosphorus promotion also make the hydrocracking process more efficient.
I'm Tang Moon, so I will be presenting how delay cooking process in order to increase refining yield in residual oil processing. So, delay cooking is an oil refinery process that converts the residual oil into low molecular weight hydrocarbons gases, naphtha, light and heavy gas oil, and petroleum coke. The process thermally cracks the long-chain hydrocarbon molecules into shorter chain molecules and leaving behind the excess carbon in the form of petroleum coke. During the process, the coker fractionator first receives and separates the feedstock. Fuel gas, naphtha, light coker gas oil, and heavy coker gas oil side draws from the fractionator and recovered. Then, the coker furnace heat the heavy liquid material from the bottom of the fractionator to about 900 to 945 degrees Fahrenheit. This heating causes the heavy liquid material to crack or change into a combination of smaller molecule gas and liquid products. During this stage, steam is injected to minimize the cracking. Next, in the operating coke drum, the material from the coker furnace is injected into the bottom and it is further cracked into gaseous products and petroleum coke that solidifies in the drum. So, after cooking, the coke drum is full of coke and it is then removed using water jets. In overall, in order to increase refinery yield in residual oil stream processing, operating coke drum at low pressure is gaining momentum in view of maximizing the liquid product yield. Table 7 shows the effect of low pressure and low recycle on coking yield of a typical feed. Next improvement. The fractionator operated at low pressure is able to maximize distillate yield, but the fractionator's sizing and specification will be affected. For example, for 0.1 megapascal pressure, a diameter of 3.96 meter fractionator is required, as opposed to 3.65 meter fractionator for 0.17 megapascal pressure operation. Next improvement. The fractionator operated at low pressure is able to maximize distillate yield, but the fractionator sizing and specification will be affected. For example, for 0.1 megapascal pressure, a diameter of 3.96 meter fractionator is required, as opposed to a diameter of 3.65 meter for 0.17 megapascal pressure operation.
Hi, my name is Yong Zutin. Today I'll be talking about the process of whisk breaking to increase the yield in oil residue stream processing.
So whisk breaking or viscosity breaking is a mild form of thermal cracking to produce naphtha, gas oil residue. The reaction occurring in the process includes cracking of long-chain paraffin and aromatic into light hydrocarbons. So let's move to the process flow diagram. Whisk breaker feed is pumped through preheat exchangers before entering the furnace, where the residue is heated to the required cracking temperature. Furnace effluent is sent to the soaker drum, where most of the thermal cracking and viscosity reduction takes place under controlled condition. The pressure in the soaker drum can be adjusted, which result in a change in residence time and the amount of heavies that reside in the liquid phase. This flexibility in pressure provides the possibility to reach optimal selectivity. Soaker drum effluent is then quenched before entering the fractionator. The vapor are then fractionated into gas, naphtha, gas oil, and whisk breaker residue. So the last one is the adding hydrogen donors in the whisk breaking process can be an alternative to improve distillate yields when upgrading heavy crude oil residues. Hydrogen donor supplies the hydrogen necessary to obtain good distillates by hydrogenating the thermal cracked oils. For example, tractylene acts as a hydrogen donor, reduces coke formation as well as producing a product of reduced viscosity, pour point, and sedimentation characteristic. The process gives a substantially higher conversion of residue fuel oil to gas oil and higher products than conventional visbreaking.